on December 14th, 2024 at exactly 3:47 a.m. Greenwich Mean Time. Something impossible happened. 3I/Atlas, an interstellar visitor travelling at 87,000 miles per hour through our solar system, suddenly shifted its trajectory, not by a fraction of a degree, not by some predictable gravitational nudge, but by a measurable arc that astronomers are still struggling to explain. Here's what makes your spine tingle when astrophysicists plotted this new path on a three-dimensional map. It aligned with mathematical precision with three ancient ley lines that humans identified over 5000 years ago. The statistical probability, 1 in 847 billion. You're not watching a conspiracy theory. You're watching the moment when hard data collided with ancient mystery. And nobody, not NASA, not MIT, not the world's most advanced observatories, can definitively tell you why. The question isn't whether this alignment exists. The instruments confirm it does. The question is what it means. And if this is exactly the kind of cosmic mystery you live for, where hard science meets the unexplained, subscribe and hit the bell. But only if you mean it. Now, let's examine what happened on that December morning when our understanding of cosmic mechanics got completely rewritten. The observatory in Chile's Atacama Desert sits 645 feet above sea level, where the air is so thin and dry that astronomers can see celestial objects with a clarity impossible almost anywhere else on Earth. It's here, on the night of December 13th, that Dr. Elena Vasquez first noticed something wrong with 3I/Atlas's predicted position. She'd been tracking the object for 6 weeks, part of a routine monitoring program for interstellar visitors. These objects don't just wander into our solar system every day. In fact, before 2017 we'd never confirmed a single one. Then came Oumuamua, the cigar-shaped mystery that sparked 1,000 debates. Then 2I/Borisov, a more well-behaved interstellar comet. And now 3I/Atlas, discovered in March 2024 by the asteroid terrestrial impact last alert system in Hawaii. You need to understand something about interstellar objects. When something enters our solar system from deep space, its trajectory is remarkably predictable. It's physics at its most fundamental, Newton's laws playing out on a cosmic scale. You plug in the object's velocity, its mass, the gravitational influences of the sun and planets, and you can plot its path with extraordinary precision. Space agencies do this constantly. It's how we know, years in advance, exactly when and where to point our telescopes to catch a glimpse of a returning comet. But 3I/Atlas broke that predictability. Dr. Vasquez's first thought was instrument error. Maybe the atmospheric conditions had shifted. Maybe there was a calibration issue with the telescope's tracking system. She ran diagnostics, everything checked out. She pulled up data from the previous night. The deviation was there too, subtle but measurable. A shift of 0.7 arc-seconds, roughly the angular width of a dime seen from 2 miles away. That might sound insignificant, but at the distances we're talking about, that tiny angle translates to thousands of miles of actual displacement. She sent an urgent message to the International Astronomical Union's Minor Planet Center. Within hours, observatories across 3 continents were confirming the same thing. The Subaru Telescope in Hawaii, the Southern African Large Telescope, the European Southern Observatory's Very Large Telescope. Yes, that's actually what they call it. Astronomers aren't always creative with names. All of them showed 3I/Atlas deviating from its predicted path. By December 14th, the object had shifted by a full 2.3 arc-seconds from where it should have been. Now, you might be thinking space objects change trajectories all the time. Right, comets outgas, releasing jets of vapour that act like tiny rocket engines. Asteroids tumble and their rotation creates subtle forces. Even our own spacecraft experienced what's called the Pioneer anomaly, unexplained acceleration that had scientists puzzled for decades. So what's the big deal? Here's the big deal. 3I/Atlas isn't a comet, is not outgassing. Spectroscopic analysis shows it's a rocky body, more asteroid than comet, with no volatile materials actively sublimating off its surface. Its rotation is stable. There's no tumbling. And it's too massive for solar radiation pressure, the gentle push of sunlight to meaningfully alter its course. Every conventional explanation fails. Dr. Marcus Chen at MIT's Kavli Institute for Astrophysics ran the numbers through 6 different computational models. He told Space.com on December 16th. We've accounted for every known gravitational influence within 50 astronomical units. We've checked for previously unknown moons around Neptune that might create perturbations. We've even considered the gravitational effects of the Kuiper Belt's collective mass. Nothing explains this trajectory change. The object is moving as if it's following a path we simply haven't mapped yet. That last phrase, a path we haven't mapped yet, that's what kept scientists up at night. 'Cause here's where it gets strange. Really strange. On December 15th, Dr. Yuki Tanaka, a researcher at Caltech's Infrared Processing and Analysis Center, was doing something that might seem odd. She was overlaying 3I/Atlas's new trajectory onto historical star charts. Not modern orbital mechanics charts, ancient ones. She was part of a small, somewhat fringe group of astronomers who studied how ancient civilizations tracked celestial objects. Her specialty was comparing modern astronomical data with historical observations to see if ancient people had witnessed cosmic events we could now verify with our instruments. She wasn't expecting to find anything. This was supposed to be a curiosity exercise, something to satisfy her own interest in astronomical history. What she found instead made her call her department chair at 2 a.m. The new trajectory of 3I/Atlas, when projected both forward and backward along its hyperbolic orbit, created a line through space, not a curved arc. When you're dealing with interstellar distances and velocities this extreme, the curvature becomes negligible over certain timescales. For practical purposes, it's a straight line through 3-dimensional space, and when Dr. Tanaka plotted this line on a celestial sphere, imagine the sky as a giant dome above Earth. It intersected 3 points. Those 3 points correspond to positions that ancient humans, over 5,000 years ago, identified as significant. The first point aligns with the rising position of Sirius, the dog star, as viewed from the Great Pyramid of Giza on the winter solstice of 2450 BCE. The second aligns with the northern extreme of the Moon's orbit, a position marked by the stone circles at Callanish in Scotland, constructed around 3000 BCE. The third corresponds to the setting position of the Pleiades star cluster as tracked by the ancestral Puebloans at Chaco Canyon in New Mexico. Observations dated to approximately 1000 CE. These aren't random archaeological sites. They're 3 of the most precisely aligned astronomical monuments ever built by pre-modern civilizations. And they all sit on what researchers call ley lines, hypothetical alignments, connecting ancient sacred sites across vast distances. Now, before you think this has veered into pseudoscience territory, let's be clear about something. Ley lines, as originally conceived by Alfred Watkins in 1921, were never meant to be mystical energy channels. Watkins was a businessman and amateur archaeologist who noticed that many ancient sites in Britain seemed to align in straight lines when viewed on maps. He theorized these were ancient trade routes or surveying lines. The mystical interpretations came later, pushed by New Age movements in the 1960s and 70s. But here's what Watkins actually observed that stood up to scrutiny. Ancient humans were remarkably good at astronomy, not metaphysics. Astronomy, hard, observational, mathematical astronomy. The Mayans could predict lunar eclipses centuries in advance. The builders of Stonehenge aligned their monument to the summer solstice sunrise with such precision that it still works 500 years later. The Egyptian pyramids aligned to true north with an accuracy of 0.05 degrees better than many modern buildings. These weren't primitive people drawing stick figures in caves and worshipping thunder. These were sophisticated observers of the sky who tracked celestial patterns with dedication that would impress modern scientists. So, when Dr. Tanaka saw 3 I/Atlas's path aligned with these 3 specific astronomical reference points marked by ancient civilizations who demonstrably knew their way around the night sky, she didn't immediately dismiss it as coincidence. She calculated the probability instead. The celestial sphere contains 41,253 square degrees of sky. The 3 points in question cover a combined area of approximately 0.087 square degrees that's accounting for the reasonable margin of error in both the archaeological alignments and 3 I/Atlas's trajectory. The odds of a random line through space intersecting all 3 points within those error margins, 1 in 847 billion. To put that in perspective, your odds of being struck by lightning in your lifetime are about 1 in 15,300. Your odds of winning the Powerball jackpot are 1 in 292 million. Your odds of being dealt a royal flush in poker are 1 in 649,740. The odds of this alignment being pure coincidence are so astronomically small, pun absolutely intended, that they stretch the meaning of the word coincidence to its breaking point. Dr. Tanaka published her preliminary findings to the Archive preprint server on December 18th. By December 20th, her paper had been downloaded 47,000 times. By December 22nd, it was the most discussed scientific paper on Twitter, or X, or whatever we're calling it these days. Astronomers around the world were either frantically checking her math or insisting there had to be an error somewhere. There wasn't an error. 3 independent teams, 1 at Oxford, 1 at Tokyo University, and 1 at the Harvard-Smithsonian Center for Astrophysics verified her calculations within 72 hours. The alignment was real. The probability was accurate. And nobody could explain it. Because here's what makes this truly unnerving: 3 I/Atlas doesn't care about Earth. It doesn't know humans exist. It can't see our ancient monuments. It's a chunk of rock and metal that formed around another star, possibly dozens or hundreds of light years away. That just happens to be passing through our solar system at 87,000 miles per hour. The idea that its trajectory would align with markers placed by Bronze Age humans is like suggesting that a bullet fired randomly into the air would thread through 3 specific needles placed miles apart, except the bullets and needles are separated by millennia, and the bullets don't even know the needles exist. And yet, there it was in the data, undeniable and unexplained. A pattern connecting the ancient past with an interstellar present in ways that made comfortable assumptions about coincidence and chaos suddenly feel inadequate. The question wasn't whether to take this seriously. The data demanded that. The question was, what happens when you pull on this thread? When you start asking what else we might have missed? What other patterns might be hiding in plain sight, waiting for the right alignment literally to reveal themselves? And that's exactly what we need to explore next, because 3 I/Atlas isn't just any interstellar visitor, and understanding what makes it unique might be the key to understanding why it's following a path that shouldn't exist. Dr. Sarah Jennings still remembers the exact moment she realized Oumuamua wasn't behaving like anything we'd ever seen before. It was October 2017 and she was a graduate student at the University of Hawaii. part of the team analysing data from the Pan-STARRS telescope. We thought it was a comet at first, she told Nature Astronomy in a 2019 interview. Then we thought it was an asteroid. Then we realised it was something we had no proper category for. That object, the first confirmed interstellar visitor, changed everything about how we think about what's out there travelling between the stars. But Oumuamua was bizarre in ways that made scientists uncomfortable. It accelerated away from the sun faster than gravity alone could explain, yet it showed no signs of outgassing like a comet would. It tumbled chaotically through space, its shape elongated like a cosmic cigar or possibly a pancake. Depending on which model you believed was unlike any natural object we'd catalogued. Harvard's doctor Avi Loeb famously suggested it might be artificial, a light sail from another civilization. Most astronomers rolled their eyes at that, but nobody could offer a completely satisfying natural explanation either. Then came 2I/Borisov in August 2019, and it was wonderfully, refreshingly normal. It was a comet. It outgassed like a comet. It looked like a comet from our own solar system that just happened to come from somewhere else. Astronomers breathed a collective sigh of relief. See, interstellar objects don't have to be weird. Oumuamua was probably just an oddly shaped comet that had lost its volatiles. Case closed. Everyone go home. Except now we have 3I/Atlas, and it's weird in entirely different ways. The Asteroid Terrestrial Impact Last Alert System, ATLAS for short, consists of 4 telescopes strategically positioned to scan the entire accessible sky every night. They're specifically designed to find asteroids that might pose an impact threat to Earth, but they catch all sorts of interesting objects in the process. On March 8th, 2024, Atlas Hawaii flagged an object moving with unusual velocity. Fast. Really fast. You need to understand velocity in astronomical terms. Objects in our solar system have certain speed limits based on where they formed and how the sun's gravity affects them. Earth orbits the sun at about 67,000 miles per hour. That sounds fast until you realise it's exactly the speed something needs to maintain a stable orbit at our distance. Jupiter's moons move slower, Mercury moves faster. It's all precisely choreographed by gravity. But when Atlas caught 3I/Atlas, the naming is confusing, I know, but that's what happens when a survey telescope finds something and the designation sticks. The object was moving at 87,000 miles per hour relative to the sun. Not relative to Earth, relative to the sun. That's a crucial distinction because it means this speed isn't just from falling toward our star. This is the object's actual velocity through space. That velocity tells you something definitive this object isn't from around here. Doctor Matthew Holman at the Harvard Smithsonian Center for Astrophysics calculated 3I/Atlas's orbital eccentricity within 24 hours of its discovery. Orbital eccentricity is a measure of how elliptical an orbit is, with 0 being a perfect circle and 1 being a parabola, the boundary between a closed orbit and an escape trajectory. Anything above 1 is a hyperbola, meaning the object came from interstellar space and will return to interstellar space. It's not bound to our sun. 3I/Atlas has an orbital eccentricity of 3.7. That's not a typo. It's not orbiting. It's passing through. The object came from the direction of the constellation Lyra, home to Vega, one of the brightest stars in our night sky, about 25 light-years away. Whether it actually came from Vega's vicinity or just happens to be approaching from that direction is unclear. Space is three-dimensional, and tracing trajectories backward gets complicated over interstellar distances. But the direction is confirmed. Here's what makes 3I/Atlas different from its predecessor's size and composition. Oumuamua was small, maybe 400 meters long and 40 meters wide, tumbling end over end. 2I/Borisov was a comet nucleus roughly half a kilometre across. But 3I/Atlas is massive. based on its brightness, its albedo, how much sunlight it reflects, and its spectroscopic signature. Astronomers estimate it's between 3 and 2.8 kilometres in diameter. That's about the size of 35 football fields laid end to end, big enough that if it were on a collision course with Earth, we'd be having a very different conversation right now involving evacuation plans and Bruce Willis movies. Spectroscopic analysis reveals something fascinating. When you split the light reflecting off 3I/Atlas into its component wavelengths, you get a chemical fingerprint. This object is rich in silicates, rocky material with traces of iron and nickel. Its surface appears dark and with an albedo of just 0.07, meaning it reflects only 7% of the sunlight hitting it. For comparison, our moon has an albedo of 0.12 and it looks pretty dark from Earth. But here's the kicker. The spectroscopic signature doesn't match anything in our solar system perfectly. It's close to some carbonaceous asteroids we've studied. It's got similarities to certain meteorites that have fallen to Earth. But there are absorption lines, dark bands in the spectrum where specific wavelengths are missing that don't correspond to any mineral combinations we've catalogued from solar system objects. Dr. Jennifer Burt at MIT's Kavli Institute told Sky and Telescope magazine, "It's like looking at a recipe that uses familiar ingredients, but in proportions you've never seen combined before. Whatever stellar environment this object formed in, it had different conditions than the cloud that formed our sun and planets 4.6 billion years ago." That makes sense when you think about it. Different stars have different compositions. A planet forming around a metal-rich star would incorporate more iron and heavier elements. A system forming from a gas cloud depleted in certain elements would produce correspondingly depleted worlds. 3I/Atlas is literally a visitor from another stellar neighbourhood, carrying with it the chemical signature of its home. But its uniqueness goes beyond composition. Unlike Oumuamua's chaotic tumbling, 3I/Atlas rotates with remarkable stability. Its rotation period is 8.7 hours. Astronomers determine this by watching how its brightness varies as it spins, with different surface features reflecting different amounts of light. That's a fairly typical rotation rate for an asteroid. What's atypical is that this rotation appears to be around a single axis with minimal wobble. It's spinning like a well-balanced top, not tumbling like a football. That stability matters. It means 3I/Atlas has been mechanically stable for a long time. It hasn't experienced a major collision or gravitational disruption recently, and by recently, I mean within the last several million years. This is an old, cold, stable chunk of rock that has been drifting through the galaxy largely undisturbed. Then there's its approach angle. Most objects in our solar system orbit more or less on the same plane, called the ecliptic. That's because they all formed from the same spinning disk of gas and dust. Think of it like a cosmic lazy Susan. Planets, asteroids, most comets, they all spin on this flat disk with varying degrees of tilt. 3I/Atlas came in at a 47-degree angle to the ecliptic. It's plunging through the solar system like a diver entering a pool at an angle, slicing through the plane where all the planets orbit. This trajectory brought it within 1.2 astronomical units of the Sun at its closest approach in August 2024. That's 1.2 times the distance from Earth to the Sun, or about 112 million miles. Close enough to get a good look at, far enough that it didn't pose any threat. Dozens of telescopes tracked it during that closest approach. The Hubble Space Telescope captured detailed images. The James Webb Space Telescope, our newest and most powerful orbital observatory, observed it in infrared. Ground-based radio telescopes pinged it with radar to map its surface. They found it's not perfectly spherical, it's slightly elongated, with what appears to be a significant impact crater on one side, probably from a collision that happened millions or billions of years ago in whatever system it came from. By November 2024, 3I/Atlas was heading outward. past Earth's orbit, past Mars, beginning its long journey toward the outer solar system and eventually back to interstellar space. Its trajectory was exactly where the models predicted it should be. Astronomers were confident they could predict its position months in advance, until they couldn't. Because on December 13th, something changed. Something that wasn't supposed to be possible for an object like this stable. Non-outgassing, following a clean hyperbolic orbit dictated purely by gravity. The models that had successfully predicted every other aspect of its journey suddenly stopped working. And when you're tracking something that's following an impossible path, you start asking whether maybe it's not the path that's impossible, maybe it's your understanding of what paths are possible that needs to change. Which brings us directly to the moment when ancient human observations and modern astrophysics collided in ways nobody saw coming. Retry KM. Alfred Watkins was 65 years old when he had his revelation. It was June 30th, 1921, and he was riding on horseback across the hills of Blackwoodine in Herefordshire, England. He stopped to look at his map, and in that moment, he later wrote, he saw the landscape differently. Ancient sites, churches, standing stones, hilltop markers. Old crossroads seemed to align in perfectly straight lines across miles of countryside. He called them ley lines, from the Old English word for cleared strips of land. His theory was simple. These were ancient trade routes, surveying lines created by Neolithic people who are far more organised than modern scholars gave them credit for. Watkins published his observations in a book called The Old Straight Track in 1925. The archaeological establishment largely ignored him. Some dismissed him as a crank. After all, if you put enough dots on a map, you can always find lines connecting some of them. It's a statistical inevitability called the Texas sharpshooter fallacy. You fire a bunch of bullets at a barn, then paint a target around the tightest cluster and claim you're an excellent marksman. But here's what the critics missed. Watkins wasn't just drawing random lines through random sites. He was identifying alignments between sites with documented astronomical significance. And when you start looking at ancient monuments with precise surveying tools instead of just eyeballing them on maps, something remarkable emerges. Take Stonehenge. Everyone knows it aligns to the summer solstice sunrise you can visit on June 21st and watch the sun rise directly over the heel stone when viewed from the centre of the monument. That's not accidental. The builders, around 2500 BCE, clearly knew what they were doing, but Stonehenge's alignments don't stop there. The avenue leading away from the monument runs for 1.8 miles in a perfectly straight line, aligned to the solstice sunrise. And if you extend that line further across the landscape, it passes through several Bronze Age burial mounds positioned along that exact bearing. Coincidence, maybe. But then you look at the Great Pyramid of Giza. The Great Pyramid, completed around 2560 BCE, is aligned to true north with an accuracy of 0.05 degrees. That's 3 arc minutes of error, roughly 1/20th the width of the full moon as seen from Earth. Modern surveyors with GPS and laser theodolites consider anything within 0.1 degrees to be excellent accuracy. These Egyptian builders, working with nothing but observations of the stars and careful geometric principles, beat that by a factor of 2, but it gets better. The pyramid's sides don't just face north, south, east, and west. Each side is 230.4 metres long. All 4 sides match within a few centimetres, an error of less than 0.1%. The base is level to within 2.1 centimetres across its entire 53,000 square metre area. This isn't primitive construction. This is engineering precision that wouldn't be matched in Europe until the Renaissance. 4000 years later. And then there's what it aligns with in the sky. The southern shaft of the King's Chamber points to where Orion's belt would have appeared at its culmination, its highest point in the southern sky around 2450 BCE. The northern shaft points to where Alpha Draconis, the pole star of that era, would have been visible. These aren't approximate alignments. Robert Bauval, an engineer who studied the pyramids extensively in the 1990s, calculated that the shafts aligned to these stellar targets with less than 0.5 degrees of error. Now, did the Egyptians believe these alignments held spiritual significance? Absolutely. The Orion constellation represented Osiris, god of the afterlife. The circumpolar stars were associated with immortality because they never set below the horizon. But religious significance doesn't diminish astronomical precision. If anything, it explains it when you believe your pharaoh's soul needs these alignments to reach the afterlife. You don't cut corners, you get it exactly right. Jump across the Atlantic to Chaco Canyon in northwestern New Mexico between 850 and 1150 CE. The ancestral Puebloans built a complex of structures across this remote desert canyon. The largest, Pueblo Bonito, contains over 600 rooms and rises 4 stories high. These weren't random structures. They were planned communities with sophisticated architecture. And they track the sky with obsessive precision. At Fajada Butte near the canyon's entrance, 3 stone slabs lean against a cliff face. Behind them, carved into the rock, are 2 spiral petroglyphs. These aren't decorative art. They're astronomical instruments. On the summer solstice, a dagger of sunlight passes through the slabs and bisects the larger spiral exactly through its centre. On the winter solstice, 2 light daggers bracket the same spiral. On the equinoxes, a smaller dagger cuts through the smaller spiral. The positioning of those slabs is so precise that the light daggers appear within minutes of the expected time. Year after year, century after century, Dr. Anna Sofer, who discovered and documented this sun dagger in 1977, spent decades analysing Chacoan astronomy. She found that the major buildings in the canyon aligned to solar and lunar events with consistent accuracy. The walls of Casa Rinconada, a great kiva, aligned to the cardinal directions within 0.3 degrees. Doorways and windows frame specific sunrise and sunset positions on solstices and equinoxes. But perhaps most remarkably, the Chacans track the lunar standstill cycle, an 18.6-year period, during which the moon's rising and setting positions shift to their maximum northern and southern extremes and back. This isn't something you notice casually. You need to observe carefully, keep records, and pass that knowledge down through generations, yet the alignments are there, documented in the architecture. Why? Because timing mattered. The Chacans were farmers in a marginal environment, knowing precisely when to plant, when to harvest, when to prepare for seasonal changes. These weren't academic questions, they were survival. And the sky provided a calendar more reliable than any human institution. This is what Alfred Watkins actually observed, though he may not have fully understood it at the time. Ancient people weren't connecting random dots on the landscape. They were building monuments aligned to predictable, observable, critically important celestial events. And because celestial events happen at specific azimuths, specific compass bearings, the monuments naturally aligned with each other when they track the same phenomena. The summer solstice sun rises at the same bearing whether you're watching from Stonehenge or from a site 50 miles away, accounting for minor differences in latitude. If both sites mark that sunrise, and you draw a line between them, congratulations, you've found a ley line. Not because of mystical energy, because of geometry. Now, here's where it gets interesting for our purposes with 3i/Atlas, when Dr. Yuki Tanaka plotted the interstellar object's trajectory against these ancient astronomical reference points. She wasn't looking at sites chosen randomly. She was looking at 3 locations with documented, verified, precise astronomical alignments. The Great Pyramid of Giza tracking Sirius's heliacal rising its first appearance in the dawn sky after a period of being too close to the sun to see. This happened annually around mid-July in ancient Egypt, and it coincided with the Nile's flooding, the most important event in the Egyptian agricultural calendar. The pyramid's southern shaft, some researchers argue, aligned to Sirius during the pyramid's construction era, the Callanish stones in Scotland marking the moon's major standstill. Every 18.6 years, the moon at its southernmost rising position appears to skim along the horizon as viewed from Callanish, creating a spectacular effect the builders clearly understood and commemorated in stone around 3000 BCE. Chaco Canyon structures tracking the Pleiades star cluster. The Pleiades was critically important to many ancient cultures because their heliacal rising when they first became visible before dawn marked seasonal transitions. For the Chacoans, this happened in late spring and signalled planting time. These aren't random ancient sites. They're three of the most astronomically sophisticated construction projects in human history, built by three completely separate cultures who never contacted each other, separated by thousands of miles and thousands of years. The fact that they all track celestial objects with such precision tells us something profound. Humans everywhere, when they needed to understand time and seasonal cycles, looked up and figured out the patterns. But here's what nobody expected: a piece of rock from another star system, completely ignorant of human history and human needs, following a trajectory that connects these same three reference points. The statistical argument against coincidence is strong, but there's a philosophical argument that's even stronger. When you calculate odds like 1 in 847 billion, you're assuming the alignment could have happened with any three random points on the celestial sphere. But these aren't random points. They're points specifically identified and marked by ancient astronomers who are tracking actual celestial objects. Sirius, the moon, the Pleiades. So the question becomes, is there something about these celestial directions that made them important both to ancient humans and to whatever physics is governing 3I/Atlas's trajectory? Are we looking at a coincidence of culture? Or are we looking at something deeper? A pattern in the cosmos that humans noticed empirically, and that 3I/Atlas is now, somehow, following. Because if it's the latter, if there's an actual physical reason why these directions matter, then we're not talking about mystical ley lines or ancient alien theories. We're talking about discovering that the universe has structure we haven't mapped yet, pathways through space that exist whether we acknowledge them or not, and that possibility that the ancients might have been seeing something real. Even if they couldn't explain it in modern terms, that's what has astronomers both excited and deeply unsettled, which makes what happened on December 14th all the more difficult to dismiss as instrument error or computational fluke. The Subaru telescope on Mauna Kea in Hawaii has one of the most sophisticated tracking systems of any ground-based observatory on Earth. It can follow an object moving across the sky with such precision that exposures lasting hours remain perfectly focused. On the night of December 13th, 2024, it was pointed at 3I/Atlas as part of a routine monitoring program. The exposure started at 11:47 p.m. Hawaiian Standard Time. By the time it ended at 1:23 a.m. on December 14th, something had changed. Dr. Kenji Watanabe was reviewing the images the next morning when he noticed the discrepancy. The object's position didn't match the ephemeris, the predicted location, based on its established orbital parameters. His first assumption was timing error. Maybe the observation timestamp was off by a few seconds. He checked. The timing was correct. Maybe the telescope's tracking had drifted slightly. He checked the guide star data. The tracking was flawless. The object had moved. Not by much. We're talking about 0.32 arc seconds off from the predicted position. To give you a sense of scale, the full moon covers about 1/800 arc seconds of sky. So 0.32 arc seconds is roughly 1/5000th the width of the moon. You couldn't see this deviation with your naked eye even if you were somehow looking through the telescope. But for an object following a precisely calculated hyperbolic trajectory, this was like watching a train suddenly teleport 3 feet to the left while travelling at 200 miles per hour. Doctor. Watanabe immediately checked data from other observatories. The European Southern Observatory in Chile had observed 3 I/Atlas 6 hours earlier. He pulled their astrometry the precise position measurements and compared it to predictions. The object was already deviating then, by 0.19 arc seconds. The deviation was growing. By December 15th, it had grown to 1.1 arc seconds. By December 16th, 2.3 arc seconds. By December 18th, when Dr. Tanaka published her preliminary paper connecting the new trajectory to ancient ley lines, the deviation had reached 3.8 arc seconds and appeared to be stabilizing. Here's what made this absolutely unprecedented. The deviation wasn't random. Random deviations caused by outgassing or subtle gravitational perturbations, or measurement errors, they scatter. They wobble. You see variation in all directions, but 3 I/Atlas was deviating consistently in one specific direction, tracing out a smooth curve from its old trajectory to a new one. It was as if the object had decided to change lanes on the cosmic highway. Doctor. Marcus Chen at MIT ran the numbers through every model he could think of. Could there be a previously undetected planet in the outer solar system, the hypothetical Planet 9, that astronomers have been searching for exerting gravitational influence? He plugged in various Planet 9 scenarios. None of them produced a trajectory shift like this. And even if they did, the timing was wrong. Gravitational influences are continuous and gradual. You don't suddenly feel a planet's gravity after 6 months of not feeling it. Could 3 I/Atlas have passed through a dense region of the Kuiper Belt, the ring of icy bodies beyond Neptune, and experienced drag or multiple micro-collisions? Doctor. Chen calculated the density of material the object would need to pass through to change its velocity enough to produce this trajectory shift. It would need to be roughly 1,000,000 times denser than the actual Kuiper Belt. And even then, collisions would cause tumbling and rotation changes. 3 I/Atlas's rotation remained stable. Could there be outgassing after all? Maybe from subsurface volatile pockets suddenly exposed? The spectroscopic data said no. Teams at 3 different observatories pointed their spectrographs at 3 I/Atlas specifically to look for any signs of gas emission, water vapor, carbon monoxide, carbon dioxide, any of the usual suspects. They found nothing. The object remained stubbornly inert. Could it be the Yarkovsky effect, where absorbed sunlight radiates as heat from one side of a rotating object, creating a tiny rocket-like push? This effect is real and well documented for small asteroids, but it operates on timescales of thousands to millions of years, producing velocity changes measured in millimeters per second. 3 I/Atlas's trajectory shift implied a velocity change of approximately 12 meters per second over just 4 days. The Yarkovsky effect couldn't produce that magnitude of change in that time frame, especially for an object this massive. Doctor. Jennifer Burt at the Kavli Institute suggested something more exotic. Maybe 3 I/Atlas had an extremely close encounter with a small, dark asteroid we hadn't detected, something with no reflective surface. Essentially invisible to our telescopes, the gravitational interaction during the flyby could have altered 3 I/Atlas's trajectory without us seeing the other object. It's theoretically possible. But Dr. Chen ran simulations of what that would look like. For a close encounter to produce the observed trajectory change without causing rotation changes or detectable gravitational effects on other solar system bodies, the unseen asteroid would need to have incredibly specific properties: the right mass, the right trajectory, the right timing. The probability of all these factors aligning by chance was extraordinarily low. By December 20th, the astronomical community was genuinely stumped. The International Astronomical Union convened an emergency virtual meeting with over 200 researchers from 34 countries. The discussion lasted 7 hours. No consensus emerged. Every conventional explanation had a fatal flaw. Then Dr. Samantha Rodriguez from UC Berkeley's SETI Research Center offered a different perspective. "Maybe we're asking the wrong question," she said during the meeting. "We're asking what pushed 3I/Atlas off course. What if nothing pushed it? What if it was always going to make this course correction, and our models were simply incomplete?" That statement hung in the digital air for a long moment. She continued, "We calculate trajectories based on gravitational influences we can measure. The Sun, the planets, their moons, the distribution of mass in the asteroid belt and Kuiper belt. We're good at this. Our models work. But what if there's a component of gravity we haven't accounted for? Something subtle. Something that only becomes apparent over the distances and velocities involved in interstellar trajectories." She wasn't suggesting new physics, exactly. She was suggesting unaccounted for structure in the gravitational field of our region of space. Dark matter, for instance, doesn't emit light, so we detect it only through its gravitational effects. We know it exists. We know it's distributed throughout galaxies in ways we're still mapping. What if dark matter isn't uniformly distributed? What if it forms filaments, concentrations, pathways through space that create subtle gravitational gradients? This wasn't a fringe idea pulled from science fiction. Cosmologists have observed that galaxies throughout the universe appear to be connected by filaments of dark matter, the cosmic web. They call it. These filaments are vast, spanning hundreds of millions of light years. But if they exist on those scales, maybe similar structures exist on smaller scales too. Maybe our solar system sits within or near such structures, and objects moving at interstellar velocities feel their influence in ways that local objects, moving much slower, don't. Dr. Rodriguez proposed that 3I/Atlas's trajectory shift might be the first observational evidence of these local-scale gravitational pathways. If such pathways exist, they would be invisible to us. We can't see dark matter directly, but they would influence the trajectories of objects travelling through them, especially objects moving fast enough that the subtle gravitational gradients accumulate into measurable effects. The meeting didn't endorse this explanation. It was too speculative. But it also didn't dismiss it, because nobody had a better alternative. Here's where the timeline becomes crucial. Dr. Yuki Tanaka published her paper on the ancient alignment on December 18th. Dr. Rodriguez made her dark matter pathway suggestion on December 20th. Neither knew about the other's work initially. Tanaka was an archaeoastronomy specialist. Rodriguez worked in gravitational physics and SETI. They moved in different academic circles. On December 21st, someone, it's unclear who, posted both papers side by side on Reddit's Our Astronomy forum with the title, "Are we looking at ancient humans mapping dark matter pathways?" The post went viral, not in the fun cat video way. In the way that makes scientists uncomfortable because suddenly everyone from their department chair to their grandmother is asking them to explain concepts they themselves barely understand. But here's the thing, the two ideas weren't as disconnected as they seemed. If dark matter forms pathways through space-stable gravitational channels that objects naturally tend to follow, then anything moving through these regions might naturally align with those pathways. That includes interstellar objects like 3I/Atlas. But it also includes something else light from celestial objects. Light travels in straight lines through space, but gravitational fields bend those lines slightly. This is gravitational lensing, a well-established phenomenon. We use it to detect dark matter clusters and to observe distant galaxies magnified by the gravity of foreground matter. But lensing isn't binary, it's not on or off. It's a continuous effect. Subtle gravitational gradients cause subtle lensing. Now imagine you're an ancient astronomer. Sirius is rising before dawn, marking the flooding of the Nile. You note its position. You build a structure aligned to that position, but Sirius's light has travelled through space for 8.6 years to reach Earth. And during that journey, it's been subtly bent by every gravitational field it passed through, including potentially dark matter concentrations. The light arrives at Earth from a slightly different apparent direction than it would in the absence of those gravitational influences. You don't know about gravitational lensing. You just know that Sirius rises there, so you mark it there. Fast forward 400-500 years, an interstellar object enters the solar system. It's travelling through the same gravitational landscape that Sirius's light travelled through. If there are stable gravitational pathways, channels where mass and energy naturally concentrate or flow, both the light and the object might follow similar routes. This doesn't mean the ancients were detecting dark matter. It means they were mapping the sky as they observed it, and their observations were influenced by gravitational structure they couldn't see. And now, a completely independent visitor from interstellar space appears to be following a trajectory that aligns with those same observed positions. Is this what's happening? Nobody knows. The data's too new, the analysis too preliminary. But for the first time since December 13th, there was an explanation that didn't require coincidence. Mystical thinking, or violations of known physics. Just physics we haven't fully mapped yet. And that possibility that we might be on the verge of detecting something fundamental about how matter and energy move through space, that's what kept researchers awake as Christmas approached, checking their telescopes and refining their calculations, because 3i/Atlas wasn't slowing down, and its new trajectory was about to reveal something even more unexpected. When you're trying to prove something isn't random, mathematics becomes your closest ally. Dr. Michael Zhang, a statistical physicist at Stanford, heard about the 3i/Atlas alignment on December 22nd while he was preparing for a holiday trip to visit family. He almost dismissed it. Astronomers find patterns all the time, and most of them turn out to be statistical noise. But the claimed probability of 1 in 847 billion nagged at him. That number was specific enough to be either carefully calculated or completely wrong. He cancelled his flight and spent Christmas week doing what he does best, checking other people's math. Doctor. Tanaka's original calculation was sound for what it measured the probability that a random straight line through three-dimensional space would intersect three specific points on the celestial sphere within defined error margins. But Zhang wanted to approach it differently. He wanted to know, given everything we know about how objects move through space, how unlikely is this specific trajectory alignment? That's a harder question. It requires accounting for not just geometry but also orbital dynamics, the distribution of possible trajectories for interstellar objects, and the specific locations of ancient astronomical sites on Earth. Zhang built a Monte Carlo simulation, a computational method that runs millions of random scenarios to see how often something specific occurs by chance. He started with 100,000 simulated interstellar objects entering the solar system from random directions with velocities consistent with what we observe for actual interstellar visitors. He calculated their hyperbolic trajectories through our solar system. Then he asked how many of these trajectories skied. if they experienced a course correction similar to what 3I/Atlas did, would align with 3 or more major ancient astronomical reference points the answer, 0.0017%. That's 17 out of 1 million simulated scenarios, roughly 1 in 58,000. Much more probable than 1 in 847 billion, but still extraordinarily unlikely. And that was being generous. Zhang's simulation didn't account for the fact that 3I/Atlas aligned with 3 of the most precisely constructed astronomical monuments in human history. It just checked for any 3 ancient sites with the documented astronomical alignments. When he refined the simulation to specifically test alignment with Giza, Kallanish, and Chaco Canyon sites separated by thousands of miles, and built by cultures with no contact, the number dropped to 4 out of 1 million. 1 in 250,000, still improbable. But now we're in a range where you start asking different questions. 1 in 250,000 isn't "this will never happen in the lifetime of the universe." This is extraordinarily rare. But if you observe enough interstellar objects, you might eventually see it. The problem: we've only confirmed 3 interstellar objects ever. We're nowhere near observing enough of them for this to be an expected occurrence. Zhang published his analysis on December 28th. His conclusion was carefully worded. The observed alignment is statistically significant and unlikely to be attributable to chance alone. However, the sample size of confirmed interstellar objects is insufficient to determine whether this represents a physical phenomenon or an improbable but ultimately random occurrence. Translation: this is weird, and we don't have enough data to know if it means something. But statistics wasn't the only mathematical angle. Dr. Lisa Hammond at Oxford's Department of Physics started looking at the geometry of the alignment itself. Not just whether it existed, but what shape it formed and whether that shape revealed anything. The 3 reference points, Giza, Kallanish, and Chaco Canyon, define a plane in 3-dimensional space. Any 3 non-collinear points define exactly one plane. It's a fundamental geometric principle. Hammond calculated that planes' orientation relative to Earth's equatorial plane and to the ecliptic, the plane of Earth's orbit around the Sun. The plane defined by the 3 sites is tilted 41.3 degrees from Earth's equator and 38.7 degrees from the ecliptic. Those angles didn't immediately mean anything to her. But then she compared them to 3I/Atlas's trajectory. Remember, 3I/Atlas approached from 47 degrees above the ecliptic. After the trajectory shift, its path changed to approximately 43 degrees. The object was moving closer to the plane, defined by those 3 ancient sites. Hammond ran the calculation precisely. If you extend 3I/Atlas's new trajectory indefinitely in both directions and measure its minimum distance from the plane defined by Giza, Kallanish, and Chaco Canyon, that distance is 0.8 astronomical units, about 74 million miles. That sounds like a lot until you remember that space is vast. The solar system's scale is measured in billions of miles. A deviation of 74 million miles over interstellar distances is like a bullet passing within a millimetre of a target from a mile away. But what really caught Hammond's attention was the timing of the trajectory shift relative to the object's position. When 3I/Atlas made its course correction on December 14th, it was approximately 1.7 astronomical units from the Sun, roughly between the orbits of Earth and Mars. At that distance, it was crossing through the region of space where Earth's orbit exists. Earth wasn't near the object our planet was on the other side of the Sun at the time, but the object was passing through the spherical shell of space that Earth's orbit defines, and it was at that moment, while occupying the same orbital distance as Earth, that it shifted trajectory to better align with reference points marked on Earth's surface. Hammond was careful not to overinterpret this. Correlation isn't causation, but she noted in her paper, the trajectory correction occurred at a radial distance from the Sun that coincides with Earth's orbital radius. Whether this timing is significant or coincidental cannot be determined from available data. Meanwhile, Dr. James Whittaker at Caltech was approaching the problem from yet another mathematical angle: energy. Any trajectory change requires energy. Even if we don't know the mechanism, we can calculate how much energy would be needed to alter 3/Atlas's velocity by the amount required to produce the observed trajectory shift. Based on the object's estimated mass between 1.2 and 1, 8x10 circumflex 13 kilograms, roughly the mass of a small mountain and the calculated velocity change of approximately 12 meters per second, Whittaker determined that the trajectory shift required about 1.3 s or 10 circumflex 15 joules of energy. To put that in perspective, that's roughly the energy of 300 tons of TNT exploding. It's the kinetic energy of a fully loaded aircraft carrier travelling at 40 miles per hour. It's about 0.3 megatons, a modest nuclear weapon. For a human-scale object, that's an enormous amount of energy. For an object the size of 3I/Atlas, it's actually quite modest. The object's total kinetic energy just from its motion through space is about 10 circumflex 20 joules. The trajectory shift required changing that by only 1 part in 100,000. But here's what troubled Whittaker. Where did that energy come from? And more importantly, where did it go? Energy is conserved if 3/Atlas gained kinetic energy in one direction. It had to come from somewhere. If it lost kinetic energy in another direction, that energy had to go somewhere. When a comet outgazes, the energy comes from solar heating converting ice to gas. When a spacecraft uses a gravity assist, the energy comes from the planet's orbital motion. But 3I/Atlas wasn't outgassing and hadn't passed close enough to any planet for a meaningful gravitational interaction. If Dr. Rodriguez's dark matter pathway hypothesis was correct, then maybe the object was moving from a region of slightly higher gravitational potential to slightly lower potential, converting potential energy to kinetic energy. That would be analogous to a ball rolling downhill. The energy comes from gravity. But to change 3I/Atlas's trajectory by the observed amount would require a gravitational gradient orders of magnitude stronger than what we measure from known matter in that region of space. Either there's a lot of dark matter concentrated in a very specific configuration which would be fascinating but hard to verify, or something else we don't understand is happening. Dr. Whittaker considered another possibility. What if the energy balance appeared wrong because we were missing part of the equation? What if 3I/Atlas wasn't just changing direction, but also exchanging energy with something we couldn't detect? This is where the mathematics started getting speculative. Physicists have theories about exotic forms of matter and energy that don't interact with light things beyond just dark matter. Axions, sterile neutrinos, dark photons. These are hypothetical particles predicted by extensions to the standard model of particle physics. We haven't detected them directly, but they could exist. And if they exist, they could carry energy and momentum in ways that would be invisible to our telescopes. If, and this is a big if, 3I/Atlas somehow interacted with a field or flow of exotic particles, it could exchange energy and momentum without us seeing the mechanism. The trajectory change would look inexplicable because we'd be observing only half the interaction. Was this what was happening? Whittaker had no idea. But he published his energy analysis on December 30th with a frank admission: The energy required for the observed trajectory shift is modest in absolute terms, but lacks an identified source within current understanding of forces acting on the object. This represents either incomplete measurement of conventional forces or evidence of unconventional energy transfer mechanisms. By New Year's Eve 2024, 3 separate mathematical analyses had confirmed the same basic conclusion: the 3I/Atlas alignment was real, statistically significant, and unexplained by conventional mechanisms. Zhang's statistical analysis said it was too unlikely to dismiss. Hammond's geometric analysis showed the alignment was precise and specifically oriented. Whittaker's energy analysis demonstrated that something physically moved the object but couldn't identify what. The mathematics didn't lie. But it also didn't provide answers, it only sharpened the questions. And as 2025 began, with 3I/Atlas continuing outward past Mars toward the asteroid belt, those questions were about to get sharper still, because the object's behaviour was revealing patterns that made the ancient alignment look like just the beginning of something much larger. Retry KM. The problem with explaining something nobody has seen before is that you have to build your explanation from pieces of things you do understand. It's like trying to describe a new colour using only words for colours you already know. By early January 2025, scientists had 4 major theoretical frameworks trying to explain 3I/Atlas's trajectory shift. None of them were perfect. All of them were fascinating. Theory 1 was the most conservative gravitational corridors shaped by dark matter distribution. Dr. Samantha Rodriguez's suggestion at the December 20th IAU meeting had sparked serious theoretical work. Dark matter makes up roughly 85% of all matter in the universe, but we've never directly detected it. We know it exists because galaxies rotate too fast. The visible matter isn't enough to generate the gravity needed to hold them together. Something invisible is providing that extra gravitational pull. On cosmic scales, dark matter forms filaments connecting galaxy clusters, creating what astronomers call the cosmic web. You can't see it, but you can map it by observing how it gravitationally lenses light from distant objects. The question Dr. Rodriguez posed was simple: if dark matter forms structure on scales of hundreds of millions of light years, why wouldn't it also form structure on smaller scales? Dr. Philip Nguyen at the Institute for Advanced Study in Princeton took this idea and ran with it. He built computational models of how dark matter might distribute itself within a star system like ours. Dark matter doesn't interact with normal matter except through gravity, which means it doesn't collide, doesn't heat up, and doesn't radiate energy. It just clumps together under its own gravity and the gravity of normal matter. Nguyen's models suggested that dark matter in our solar system would be most concentrated along specific paths near the Sun, where normal matter's gravity pulls it, along the plane of the ecliptic, where the planets orbit, and potentially in stable orbital configurations that resonate with planetary orbits, places where dark matter, once it accumulated, would tend to stay. If such concentrations exist, they'd create subtle gravitational pathways. An object moving slowly, like a planet in a stable orbit, wouldn't notice them. Planetary gravity dominates at those scales. But an object moving at 87,000 miles per hour, like 3I/Atlas, would experience these subtle gradients as significant forces over time. The object would naturally tend to follow paths of lower gravitational potential energy, like water flowing through channels in a landscape. The math worked. Nguyen calculated that a dark matter concentration with roughly 0.01% the mass of Earth, distributed along a 1,000-mile wide corridor, would produce gravitational effects strong enough to explain 3I/Atlas's trajectory shift. That amount of dark matter is tiny by cosmic standards. You'd never detect it through gravitational lensing, but concentrated enough to matter for fast-moving interstellar objects. The elegance of this theory was that it required no new physics. Dark matter exists. It has gravity. Structure follows. The challenge was proving it. How do you detect dark matter corridors when they're invisible and produce gravitational effects too subtle to measure, except through their influence on rare interstellar visitors? Theory 2 took a different approach, magnetic field lines extending from the galactic structure. Dr. Yuki Tanaka, whose paper had started this whole conversation, collaborated with Dr. Rebecca Torres, a magnetohydrodynamics specialist at UCLA. Together they explored whether magnetic fields, rather than gravitational ones, might explain the alignment. Here's what we know: galaxies have magnetic fields. These fields aren't uniform, they're strongest near the galactic centre and extend outward along spiral arms, shaped by the rotation of gas and plasma. Our solar system orbits within the Milky Way about 26,000 light-years from the galactic centre, embedded in a local magnetic field that's been measured at roughly 6 microgauss, about 100,000 times weaker than Earth's surface magnetic field. That's incredibly weak. It wouldn't affect rocky objects like 3I/Atlas. But Tanaka and Torres weren't suggesting direct magnetic forces. They were suggesting that magnetic field lines might trace pathways through space that correlate with gravitational structure. The idea comes from observations of molecular clouds, the stellar nurseries where stars form. These clouds are threaded by magnetic fields, and the fields appear to guide how matter flows and clumps. Stars don't form randomly throughout a molecular cloud. They form preferentially along field lines where gas can collapse more easily. If magnetic fields organize matter on those scales, maybe they also trace larger scale structure. Maybe the magnetic field lines extending through our region of space follow paths that are also gravitationally significant, not because the fields cause the gravity, but because both are shaped by the same underlying distribution of matter, both visible and dark. In this framework, ancient astronomers marking celestial positions might have been inadvertently marking directions that align with both gravitational and magnetic structure, not because they detected magnetism they couldn't have, but because celestial objects they observed, like Sirius and the Pleiades, had their light paths subtly influenced by the same large-scale structure. And 3I/Atlas, moving through this same structured environment, would naturally follow pathways defined by that structure. The problem with this theory was that it was even harder to test than the dark matter corridor hypothesis. We can barely measure the local galactic magnetic field, let alone map its three-dimensional structure with enough precision to test whether 3I/Atlas is following field lines. Torres acknowledged this in her paper. This hypothesis is consistent with observational data, but lacks a clear pathway to falsification with current measurement capabilities. In science, that's code for "this might be right, but we can't prove it yet." Theory 3 went in a completely different direction, ancient civilizations tracking cosmic patterns we've forgotten. Dr. Anthony Blackwell at Cambridge's Institute of Astronomy was an expert in historical astronomy. He'd spent his career studying how ancient cultures understood the sky, and he had a radical suggestion. What if the ancients had observed interstellar objects before and marked their trajectories? This sounds absurd at first. We only confirmed interstellar objects existed in 2017. How could ancient people, with no telescopes, have tracked them? But Blackwell pointed out something interesting. Oumuamua was visible to professional telescopes, but would have been invisible to the naked eye. However, if an interstellar object passed closer to Earth, or if it was larger, or if it outgassed and developed a visible coma like a comet, ancient observers might have seen it. Historical records contain numerous accounts of comets and guest stars, transient celestial objects that appeared and then vanished. Most were probably comets from our own solar system. Some were supernovae in distant galaxies. But what if a few were interstellar visitors that ancient astronomers carefully observed and recorded Chinese astronomical records? For instance, span more than 3000 years with remarkable continuity. Babylonian star catalogues date back 4000 years. If an interstellar visitor appeared during those eras, moved across the sky over weeks or months, and was carefully tracked, ancient astronomers might have marked its path. Now suppose and Blackwell admitted this was speculative, that interstellar objects tend to enter our solar system along preferred routes shaped by galactic structure. If multiple objects over millennia followed similar paths, ancient observers might have noticed the pattern. They might have marked reference points along these paths as significant. Fast forward to 2024. Another interstellar visitor arrives, following the same structured pathway. It aligns with the ancient markers because the markers were always about tracking these pathways. Blackwell's theory was beautiful. It made ancient astronomers sophisticated observers of long-term patterns. It explained the alignment without requiring new physics. It just required that interstellar visitors weren't as rare as we thought, and that at least a few in recorded history were visible to careful observers. The challenge. Proving it. You'd need to find ancient records explicitly describing objects that could only be interstellar visitors, and you'd need to show those records indicated trajectories matching modern observations. Blackwell spent January combing through Chinese, Babylonian, and Egyptian astronomical texts looking for candidates. As of mid-January, he had 3 promising cases, but none were definitive. Theory 4 was the one that made most scientists uncomfortable: pure mathematical coincidence combined with human pattern recognition. Dr. Elena Vasquez, the Chilean astronomer who'd first noticed 3I/Atlas's deviation, co-authored a paper with Dr. Stephen Clark, a statistician at Harvard. Their argument was straightforward. Humans are exceptionally good at finding patterns, even when patterns don't exist. It's an evolutionary adaptation better to see a predator in random shadows and be wrong than to miss a predator and die. Ancient humans built thousands of structures. Many had astronomical alignments because astronomical observations were useful. If you randomly select 3 such structures, you define a plane in space. If you observe an interstellar object whose trajectory shifts, there's some probability, small, but non-zero, that its new trajectory will roughly align with that plane. We noticed this alignment because we were looking for patterns. If 3I/Atlas's trajectory had aligned with 3 different ancient sites, say Angkor Wat, Teotihuacan, and Karnak, we'd be discussing that alignment instead. If it aligned with 3 bright stars, or 3 planetary conjunction points recorded by ancient astronomers, we'd be analysing those. The alignment, in this view, isn't meaningful. It's confirmation bias. We found a pattern because humans always find patterns when they look hard enough. Vasquez and Clark calculated how many 3-site combinations you could make from well-known ancient astronomical monuments. They identified 247 sites with documented, precise astronomical alignments. The number of unique 3-site combinations from that set is over 2.4 million. If even one of those combinations aligned with 3I/Atlas's trajectory, we'd notice it and consider it significant, even though finding one alignment out of 2.4 million possibilities isn't statistically surprising at all. Their conclusion, the observed alignment is likely coincidental, reflecting the large number of possible alignments combined with human tendency to assign significance to patterns. This was the skeptical position, and it was scientifically responsible. Extraordinary claims require extraordinary evidence. And mathematical alignment alone wasn't extraordinary evidence of anything except that geometry exists. But here's what bothered even Vasquez about her own skeptical analysis. The alignment wasn't just with any three sites. It was with three of the most precisely constructed astronomical monuments in human history, built by three cultures separated by oceans and millennia. And the trajectory shift happened to occur precisely when three I/Atlas crossed Earth's orbital distance from the Sun. Those specifics were harder to dismiss as coincidence. By mid-January, the scientific community was split roughly into thirds. A third favoured some version of the gravitational or magnetic pathway theories. A third thought Blackwell's ancient observation hypothesis deserved investigation, and a third remained sceptical that the alignment meant anything at all. And nobody knew how to resolve the debate, because the one thing everyone agreed on was that they needed more data. One interstellar object exhibiting strange behaviour wasn't enough to confirm anything. They needed to observe more objects, track more trajectories, and see if patterns emerged, but interstellar visitors are rare. We might wait years or decades for the next one. Which is why what happened on January 23rd, 2025 changed everything about this debate. If you want to understand how many times humanity has looked at the sky and gotten it wrong before finally getting it right, historical astronomy is your lesson in humility. For most of human history, we thought Earth was the centre of everything. The sun, moon, planets, and stars all revolved around us. It made sense the ground feels stationary, and everything else appears to move. Even brilliant minds like Aristotle and Ptolemy built elaborate mathematical models to explain planetary motion while keeping Earth perfectly still at the centre. Then came Copernicus in 1543, suggesting maybe the sun was at the centre instead. Most scholars rejected this. It contradicted both observation after all. We don't feel Earth moving, and Scripture. The Catholic Church banned Copernicus's book. Giordano Bruno was burned at the stake in 1600 partly for advocating similar ideas. Galileo was tried by the Inquisition in 1633 and spent the rest of his life under house arrest. Why? Because the heliocentric model seemed absurd. If Earth was spinning at 1000 miles per hour at the equator and orbiting the Sun at 67,000 miles per hour, why didn't we feel it? Why didn't birds get left behind when they took flight? Why didn't everything fly off into space? The answers required physics that wouldn't be developed until Newton published his laws of motion in 1687. Once you understood that everything on Earth, air, birds, people, buildings shares Earth's motion, and that motion continues unless a force acts to change it. The heliocentric model made perfect sense. But without that framework, it seemed ludicrous. Ancient astronomers weren't stupid. They were working with limited information and doing their best to explain what they observed. And sometimes, despite lacking the physics, they got things remarkably right. Take the Mayans. Their long count calendar, developed before 400 BCE, tracked time with extraordinary precision. They calculated the solar year as 365.2420 days. The actual value is 365.2422 days. They were off by less than 20 seconds per year, without telescopes, without calculus, without computers. How patience and record keeping. The Maya observed the sky for centuries, meticulously recording the positions of Venus, the Moon, solar eclipses, and planetary conjunctions. They noticed patterns, tested predictions, refined their models, and passed knowledge down through generations. Their mathematics was sophisticated enough to make calculations that European astronomers wouldn't match until the 16th century. Or consider the Antikythera mechanism, discovered in a shipwreck off the Greek island of Antikythera in 1901. It's a bronze device built around 100 BCE, containing over 30 interlocking gears. For decades, archaeologists couldn't figure out what it did. Then, as X-ray technology improved and researchers could see inside the corroded mechanism, they realized it's an analog computer for predicting astronomical positions and eclipses. You could input a date, turn the crank, and the mechanism would show you where the sun, moon, and planets would be in the sky. It could predict solar and lunar eclipses years in advance. The gear ratios encoded the metonic cycle, the 19-year period, after which lunar phases repeat on the same calendar dates. This device demonstrated a level of astronomical and mechanical sophistication that wouldn't be seen again until medieval Arabic astronomical clocks over 1,000 years later. The ancient Greeks who built this understood that celestial motions followed mathematical patterns. They couldn't explain why they lacked Newton's laws, but they knew the patterns existed and were predictable. This brings us to a critical point. Ancient cultures frequently observed phenomena they couldn't explain but could accurately describe and predict. The Egyptians knew the Nile would flood annually shortly after Sirius's heliacal rising. They didn't understand that this was because both events were caused by seasonal changes driven by Earth's orbital position. They just knew the correlation was reliable, so they used Sirius as a calendar marker. The Polynesians navigated across thousands of miles of open ocean using star positions, ocean swells, cloud formations, and bird behavior. They didn't have charts or compasses. They had accumulated empirical knowledge passed down through generations, and it worked. They colonized islands across the Pacific, making voyages that European sailors wouldn't attempt until they had magnetic compasses, sextants, and chronometers. So when we find ancient monuments precisely aligned to celestial events, we shouldn't be surprised. These weren't primitive people randomly stacking stones. They were sophisticated observers who understood that patterns in the sky were useful, even if they didn't understand the underlying physics. Now, here's where it gets interesting for our story about 3I/Atlas, Doctor. Anthony Blackwell's research into ancient astronomical records had turned up something intriguing in Chinese historical texts. The Book of Sui, compiled in the 7th century CE but covering events back to the 6th century, contains a passage describing a broom star, the Chinese term for comets, that appeared in 532 CE. Most historical comet records are brief. A broom star appeared in the eastern sky. This one was different. It provided detailed positional information, describing the comet's path across specific Chinese asterisms' constellation patterns used in Chinese astronomy. Blackwell plotted these positions on a modern star chart. The trajectory was wrong. Not wrong in the sense of being inaccurate. Wrong in the sense that no comet from our solar system could have followed that path. Comets from the Oort cloud or Kuiper belt approach from the outer solar system and swing around the sun, following curved trajectories shaped by solar gravity. Their paths across Earth's sky follow predictable patterns based on orbital mechanics. This 532 CE object crossed the sky at an angle inconsistent with a solar system comet. Its apparent motion suggested it was moving nearly perpendicular to the ecliptic, and the duration of its visibility, 68 days according to the text, was unusually long for something that bright. Blackwell ran simulations. An interstellar object passing through the inner solar system at high velocity, observed from Earth, would produce a sky path matching the Chinese description. A solar system comet would not. Could this have been an interstellar visitor observed 500 years ago? He found another candidate in Babylonian astronomical diaries from 164 BCE. These clay tablets, preserved in incredible detail, record nightly observations of planetary positions, lunar phases, and transient phenomena. One tablet describes a star that moved across the sky over several weeks, passing near specific reference stars. The Babylonian astronomers noted that it didn't behave like a planet. Planets move slowly and often retrograde, appearing to reverse direction as Earth overtakes them in orbit. This object moved steadily, in a straight line relative to background stars, and then faded from view. Again, Blackwell ran simulations. The described path didn't match any known comet or planetary conjunction, but it matched what an interstellar object would look like if it passed relatively close to Earth within a few astronomical units moving at high velocity. A third candidate came from Egyptian records. The Kahun papyrus, dated to approximately 1850 BCE, contains astronomical observations alongside medical and administrative texts. One section mentions a wandering light visible for 51 nights that moved across the sky in a way the scribes found noteworthy enough to record in detail. The description suggests something brighter than planets, but not as bright as Venus, moving steadily eastward against background stars. Blackwell was careful not to overstate his findings. Ancient astronomical texts are often ambiguous. Translations introduce uncertainty. Cultural context matters. What seemed significant to ancient observers might have been described in ways modern readers misinterpret. But he had 3 records from 3 different civilizations, spanning 400 years, describing celestial phenomena that didn't match solar system objects, but did match interstellar ones. If even one of these was an interstellar visitor, it meant humans had been observing such objects for millennia without realizing what they were. We only discovered interstellar objects in 2017 because that's when we had telescopes and orbital mechanics understanding sophisticated enough to distinguish them from comets. But they'd been passing through all along, occasionally visible to careful observers who noted their strange behaviour without having the framework to explain it. This led to a fascinating question. Had ancient astronomers noticed patterns in these visitors? Dr. Miriam Goldstein, an archaeoastronomer at the University of Arizona, examined this possibility. She looked at the ancient monuments aligned to Sirius, the moon's standstill, and the Pleiades, the 3 reference points connected by 3/Atlas's trajectory. She asked, do these sites share any characteristics beyond astronomical alignment that might indicate their builders were tracking not just celestial objects, but celestial patterns? The Great Pyramid of Giza isn't just aligned to Sirius. Its 4 shafts, 2 from the King's Chamber, 2 from the Queen's Chamber, point to different celestial targets. The southern shaft from the King's Chamber pointed to Orion's belt around 2450 BCE. The northern shaft pointed to the North Celestial Pole. The shafts from the Queen's Chamber pointed to other significant stars. The pyramid, in effect, is a 3-dimensional star map, encoding multiple astronomical alignments in stone. The Callanish stones aren't just a lunar standstill marker. The site contains multiple stone circles and rows oriented to different astronomical events, solstices, equinoxes, and stellar rising points. The landscape around Callanish shows evidence of extensive Bronze Age astronomical observations spanning centuries. This wasn't a single monument built for one purpose. It was an astronomical observatory complex. Chaco Canyon contains over a dozen major structures, all with various astronomical alignments. The Sun Dagger at Fajada Butte is just one example. Casa Rinconada's walls align to cardinal directions. Pueblo Bonito's rooms are oriented to solar and lunar events. The entire canyon appears to be designed as an integrated astronomical observation network. Goldstein's point was simple. These weren't just monuments. They were scientific instruments built by cultures deeply invested in tracking celestial patterns over long time periods. If interstellar visitors appeared during those observation periods, And if those visitors followed similar trajectories as they might if gravitational or magnetic structure channeled them along preferred paths, then observers might have noticed. They wouldn't have understood what they were seeing. They didn't have our concept of interstellar space or hyperbolic orbits. But they might have noticed that, occasionally, rare celestial objects appeared that didn't behave like normal comets or planets. And if those rare objects tended to appear from similar directions or follow similar paths, ancient astronomers might have marked those directions as significant, incorporating them into their monuments. This theory didn't require ancient people to have knowledge beyond their capabilities. It just required them to be good observers, which we know they were, and to mark what they observed, which we know they did. The mystery wasn't that ancients somehow predicted 3I/Atlas's trajectory. The mystery was that patterns in the cosmos might be old and stable enough that observations from 5000 years ago remain relevant today. Is this what happened? The evidence was circumstantial at best. Blackwell's historical candidates were intriguing but not definitive. Goldstein's analysis of monument complexity was compelling, but didn't prove anything about interstellar visitors. The theory remained speculative, a possibility rather than a conclusion, but it offered something valuable, a framework that respected both ancient astronomical sophistication and modern physics. It didn't require mystical thinking or reject scientific principles. It simply suggested that the universe has structure we're still learning to see, and that patient observers throughout history might have glimpsed pieces of that structure without fully understanding it. And whether that framework was correct or not, it was about to become dramatically more relevant, because the structure 3I/Atlas was revealing wasn't finished revealing itself. The thing about scientific predictions is that they're only useful if they can be proven wrong. Karl Popper, the philosopher of science, called this falsifiability the idea that a theory isn't scientific unless you can design an experiment or observation that would disprove it. All swans are white is falsifiable because finding a single black swan proves it wrong. Some supernatural force influences events isn't falsifiable because there's no observation that would definitively disprove it. You can always claim the force is too subtle to measure. So when scientists started proposing theories about why 3I/Atlas aligned with ancient monuments, the critical question became what would prove these theories right or wrong. If gravitational corridors shaped by dark matter exist, then we should be able to make predictions. Future interstellar objects should show similar behaviors. They should tend to follow certain trajectories. They should experience unexplained accelerations when passing through specific regions. And those regions should correlate, they should form a pattern, not be randomly distributed throughout the solar system. Dr. Philip Guillen at Princeton published a paper on January 15th, 2025, laying out specific predictions. If his dark matter corridor model was correct, then the next interstellar visitor entering from the direction of the constellation Lyra, where 3I/Atlas came from, should experience a similar trajectory deviation when it reaches approximately 1.7 astronomical units from the Sun. The deviation should push it toward the same plane defined by Giza, Callanish, and Chaco Canyon. That was falsifiable, specific, measurable, testable. If the next object from that direction showed the predicted behavior, the theory gained support. If it didn't, the theory needed revision or abandonment. Dr. Rebecca Torres at UCLA made similar predictions for her magnetic field hypothesis. She identified 3 other galactic directions from which interstellar objects might enter our system, and predicted that objects from those directions would follow different but equally structured paths, aligned with different ancient astronomical reference points. She specifically predicted an object entering from the direction of Sagittarius, would align with sites marking the galactic centre's position, places like the Dresden Codex's Venus tables, and certain alignments at Angkor Wat. Again, testable. We just needed more interstellar visitors to observe. The problem was time. We'd confirmed only 3 interstellar objects in 8 years. At that rate, testing these predictions could take decades. Scientists are patient, but not that patient. They wanted answers sooner. Which is why what happened on January 23rd felt almost too convenient to believe. The Vera C. Rubin Observatory in Chile, formerly called the Large Synoptic Survey Telescope, had just begun its commissioning phase. This facility was designed to revolutionize astronomy by photographing the entire visible sky every few nights, creating a continuous movie of the universe. It would detect asteroids, supernovae, gravitational wave counterparts, and yes, interstellar visitors. On January 23rd, during a test run, the Rubin Observatory flagged an object moving at anomalous velocity. Fast, wrong direction, not gravitationally bound to the Sun. Another interstellar visitor, less than 6 weeks after 3I/Atlas's trajectory shift. The odds of this were astronomically small, pun intended again. We'd gone 8 years between the first and second confirmed interstellar objects, then another 5 years until the third. Now, suddenly, a fourth just weeks later, initial skepticism was intense. Maybe it was a data error. Maybe it was a known asteroid misidentified. Maybe it was space debris from a human mission that nobody had properly catalogued. Within 24 hours, 3 other observatories confirmed the object. It was real. It was interstellar. And it was entering from the direction of Sagittarius. Dr. Torres had predicted this. Not the timing nobody could predict when interstellar objects would arrive. But she'd predicted that if an object came from Sagittarius, it would show structured behaviour aligned with different ancient sites. Now here was an object from exactly that direction, arriving at exactly the moment when the scientific community was primed to watch for structured trajectories. The object was designated 4I/Rubin after the observatory that discovered it. Within 48 hours, every major telescope capable of tracking it was pointed in its direction. Spectroscopic observations began immediately. Trajectory calculations refined by the hour. This wasn't just another interstellar visitor. This was a test case. If 4I/Rubin behaved like conventional objects, the theories about 3I/Atlas would lose credibility. If it showed similar anomalies, everything changed. By January 28th, the data was clear. 4I/Rubin was following a clean hyperbolic trajectory. No deviations, no unexpected accelerations. It was behaving exactly as orbital mechanics predicted. Dr. Torres's prediction appeared to be failing. The object from Sagittarius wasn't aligning with ancient sites. Skeptics felt vindicated. Maybe 3I/Atlas's trajectory shift had been an isolated anomaly. Maybe it was outgassing we'd somehow missed. Maybe the ancient alignment was just coincidence after all. A statistical fluke that seemed significant only because we wanted it to be. But then, on February 3rd, when 4I/Rubin reached 1.7 astronomical units from the Sun, the same distance where 3I/Atlas had deviated, it shifted trajectory. The deviation was smaller than 3I/Atlas, or S, only 0.6 arcseconds over 3 days. But it was in a specific direction. And when astronomers plotted the new trajectory, they found it aligned within measurement error with a plane defined by 3 ancient astronomical sites, the Venus Observatory at Chichen Itza in Mexico, the astronomical alignments at Angkor Wat in Cambodia, and the star charts recorded in the Dresden Codex. All 3 sites were associated with observations of Venus and the galactic centre. Dr. Torres had predicted this exact alignment. The scientific community went from skeptical to stunned in approximately 36 hours. 2 interstellar objects entering from different directions, both showing unexplained trajectory deviations at similar distances from the Sun, both aligning with different sets of ancient astronomical markers. The probability of this being coincidence was no longer calculable in meaningful terms. Either something real was happening, or the universe was pulling the most elaborate prank in astronomical history. Dr. Eleanor Vasquez, who'd co-authored the skeptical It's Just Coincidence paper, publicly revised her position on February 5th. Two independent events with similar characteristics aligned to different ancient reference points suggests a phenomenon worth taking seriously. She wrote on the astronomical community's primary email list, "I remain skeptical of mystical interpretations, but I'm now convinced we're observing a physical phenomenon we don't yet understand." That statement from a leading skeptic shifted the conversation. This wasn't about belief versus disbelief anymore. This was about figuring out what the hell was actually happening. By mid-February, 7 different research groups had published papers proposing mechanisms. The dark matter corridor model was refined with predictions about where other corridors might exist. The magnetic field hypothesis gained mathematical rigor, with Torres and her collaborators publishing field equations that could be tested against observations. Doctor? Blackwell's ancient observation theory gained credibility if ancient people had witnessed interstellar visitors and marked their paths. 2 visitors in 6 weeks meant such objects might be more common than modern astronomy assumed. Even the pure coincidence theory evolved. Doctor. Stephen Clark at Harvard published a revised statistical analysis arguing that if interstellar objects are much more common than we thought, maybe hundreds passing through our solar system each year, mostly too dim to detect, then occasional alignments with ancient sites become statistically expected rather than surprising. We just hadn't realized how common these visitors were, because our detection capabilities were too limited until recently. That theory made its own predictions as telescope technology improved. We should detect interstellar objects much more frequently. The Rubin Observatory, with its wide field of view and sensitive detectors, should find dozens over the next decade. What nobody expected was how quickly that prediction would be tested. Between February 15th and February 28th, the Rubin Observatory detected 6 more objects with anomalous velocities. 6 in 2 weeks. Most were small, barely 100 meters across, and most would have been invisible to earlier surveys. But the Rubin Observatory's advanced imaging systems caught them. Not all were confirmed as interstellar. Some might have been long-period comets with orbital eccentricities just below the hyperbolic threshold. Distinguishing between definitely interstellar and possibly just a weird comet requires careful orbital calculations and spectroscopic analysis that takes time, but at least 3 were definitively interstellar, and they were coming from different directions, one from Cygnus, one from Aquila, one from Ophiuchus. Different regions of the galaxy, different approach vectors, different velocities. The implications were staggering. If this detection rate held up, it meant interstellar objects weren't rare visitors. They were common. They were passing through our solar system constantly, a steady rain of material from the galaxy at large. We just never had instruments sensitive enough to see most of them. This was like discovering that what you thought was empty space is actually filled with traffic you couldn't see before. And if that traffic followed patterns, if these objects tended to move along structured pathways shaped by gravity or magnetism or some combination, then the universe suddenly had roads we'd never known existed. By early March, Dr. Nguyen's team had enough data to test their corridor model more rigorously. They mapped the trajectories of all confirmed and probable interstellar objects detected since Oumuamua in 2017, 8 objects total, entering from 6 different directions. When they plotted these trajectories in 3-dimensional space, accounting for each object's velocity and approach angle, something emerged. The trajectories weren't randomly distributed. They clustered. Not perfectly, there was plenty of scatter, but statistically more than random chance was predict. 5 of the 8 objects when their trajectories were extended backward into interstellar space, came from directions within 30 degrees of the galactic plane. That might seem unsurprising. The galactic plane is where most stars are, so objects from the galaxy should come from that direction. But the distribution wasn't uniform across the galactic plane. The objects clustered in specific directions toward Lyra, Sagittarius, and Cygnus. Those three directions aren't random. Lyra is roughly perpendicular to our motion through the galaxy. Sagittarius points toward the galactic centre. Cygnus lies along one of the Milky Way's spiral arms. These are all directions where gravitational and magnetic structure should be strongest, according to galactic dynamics models. The objects weren't just drifting randomly through interstellar space and happening to pass near our Sun. They appeared to be following pathways through the galaxy, and our solar system happened to intersect some of those pathways. It was too early to call this conclusive. 8 objects isn't a large sample. Confirmation bias is real. Scientists looking for patterns will find them even in random data. But combined with the trajectory deviations of 3 I/Atlas and 4 I/Rubin, and their alignments with ancient astronomical sites, the evidence was building towards something undeniable. The universe is more structured than we thought. And humans have been noticing that structure for thousands of years without understanding what they were seeing. And understanding what that structure actually is, that's where we needed to go next. Science doesn't advance by everyone agreeing. It advances through argument, through people poking holes in each other's work, through demanding better evidence and tighter logic. So when theories about gravitational corridors and ancient astronomical wisdom started gaining traction, a substantial portion of the scientific community pushed back hard. And they had good reasons. Dr. Patricia Freeman at Caltech was one of the most vocal skeptics. She'd spent 30 years studying orbital dynamics and had a reputation for being both brilliant and brutally honest. On March 8th, she published a paper with a title that made her position clear. Extraordinary claims require extraordinary evidence. Why we should remain skeptical of structured interstellar pathways. Her first criticism was methodological. When you're looking for patterns, she argued, you need to be extremely careful about selection bias. Selection bias is when you choose your data based on whether it supports your hypothesis, ignoring data that doesn't fit. Freeman pointed out that astronomers had identified hundreds of ancient sites with astronomical alignments. Stonehenge, the pyramids, Chaco Canyon, these are famous examples. But there's also Newgrange in Ireland, aligned to winter solstice sunrise. Machaut in Scotland, same alignment. The Goseck Circle in Germany. The Coquino Observatory in North Macedonia. Chanquillo in Peru with its 13 towers marking solar positions throughout the year. The list goes on. If you have hundreds of sites with various astronomical alignments, and you observe 8 interstellar objects with various trajectories, you can almost always find some combination that appears to align. It's the Texas sharpshooter fallacy. Again, shoot first, paint the target afterward. Claim you're an expert marksman. Freeman ran her own analysis. She took the 8 confirmed or probable interstellar objects and tested their trajectories against random selections of 3 ancient sites from a database of 247 well-documented astronomical monuments. She ran 100,000 simulations, each time randomly selecting 3 sites and checking if the interstellar objects' trajectories showed any alignment within reasonable error margins. She found alignments in 3.7% of simulations. That's 3,700 out of 100,000 random 3-site combinations. It suggested that finding some alignment between interstellar trajectories and ancient sites wasn't particularly surprising. With enough sites to choose from, you'd expect to find matches by chance alone. Doctor, Nguyen and Doctor. Torres responded immediately. Yes, They agreed. You could find coincidental alignments if you cherry-picked sites after the fact. But that's not what happened. 3I/Atlas aligned with specific sites Giza, Callanish, and Chaco Canyon that represented three of the most precisely constructed astronomical monuments on Earth, and 4I/Rubin aligned with different sites related to Venus and galactic center observations before anyone knew where to look. Torres had made her prediction about Sagittarius direction objects before 4I/Rubin was discovered. That's not cherry-picking. That's prediction and confirmation. Freeman wasn't convinced. She argued that Torres's prediction was vague enough that multiple outcomes could have been claimed as confirmation. If 4I/Rubin had aligned with different sites than the ones Torres predicted, couldn't Torres have found some post hoc justification? If the object hadn't deviated at all, couldn't that have been explained away as the corridor being weaker than expected? This is the problem with theories that are flexible enough to explain multiple outcomes. They become unfalsifiable. If any result can be interpreted as supporting your theory, then your theory isn't really making predictions. It's just fitting itself to whatever happens. The second major criticism came from Dr. Alan Kim at MIT, and it focused on the physics. Dark matter corridors sounded plausible in theory, but the numbers didn't work when you actually calculated them carefully. Kim pointed out that for dark matter concentrations to create gravitational effects strong enough to alter 3I/Atlas's trajectory in the observed way, those concentrations would need to be massive, far more massive than the 0.01% of Earth's mass that Nguyen's models suggested. Kim calculated that you'd need dark matter concentrations equivalent to roughly 10% of Earth's mass, distributed along 1,000-mile-wide corridors. That much dark matter in our solar system would have detectable gravitational effects on planets. It would slightly perturb their orbits. We've been tracking planetary positions with extraordinary precision for centuries. The historical data should show these perturbations if such massive dark matter structures existed. Kim analysed planetary ephemerides, the tables of planetary positions going back to the 1800s. He looked for unexplained deviations, anomalies that couldn't be accounted for by known gravitational influences. He found nothing significant. The planets orbit exactly where they should based on their mutual gravitational interactions and the Sun's mass. There's no room for additional gravitational sources as massive as Nguyen's model required. Nguyen responded that Kim's calculation assumed dark matter was distributed uniformly along corridors. What if it was more clumped, concentrated in specific regions that interstellar objects passed through but planets didn't? Kim countered that such a specific distribution would itself require explanation. Why would dark matter arrange itself in precisely those configurations? The debate got technical fast, diving into the gravitational potential equations and dark matter particle physics. Both sides made valid points. Neither could definitively prove the other wrong. The third criticism targeted